Okay, we're on. Is it red there? Yep. Okay. Very good. Welcome to class. This is Wednesday, September 9th. Section 2 should be here. Chapter 1, we're still wrapping up. We've got a big problem to resolve. That is the Vesper shapes reconciled with what? The atomic orbitals, the S and the 3Ps there. How do we get to these tetrahedral, trigonal planar, digonal coordination states for the different simple organic molecules? So hopefully we'll figure that out today. Homework 1 is due tonight. Make sure you get that in. And I saw quiz 1 is in successfully. Thank you. We'll grade that and get the scores entered and post the key. That's the only way you're going to tell where you miss points is going to the key, and we'll post that on Learning Suite. So you'll have to look through it. If there's any grading discrepancies or regrade requests, you need to submit that to me in writing via email, addressing the key, anything that we may have misgraded, and we'll take care of that within 1 week. You need to get that request in within 1 week. So yeah, very good. And also we'll be starting chapter 2, which is acid-base chemistry. And you had a lot of acid-base chemistry in 105, 106, but we'll use acid-base theory to begin to talk about reactivity. And again, we'll use examples from OChem. So there'll be some new things there, but you will remember, of course, many of the strong acids and bases and some of the factors that you looked at in Gen Chem there to help you out with that. Any questions before we get started here? I need to pause more often and do that. Okay, very good. So here's the problem. If we can look up here, Colin, and see the overhead, there's the atomic orbitals for carbon. That doesn't help us out very much, does it? So from quantum mechanics, we get this picture here, and we know these orbitals and these energies very well from the Schrodinger equation and from spectroscopy. But this doesn't tell us anything about the geometry of how carbon adopts the different shapes we need to look at for the functional groups, okay? Double bonds and double bonds to heteroatoms, oxygen, nitrogen, and then triple bonds, and then those geometries. We get that from Vesper theory. But here we don't have very much. So we need to go forward into another level of theory. Yeah, there's quantum mechanics. There's Einstein sticking out his tongue. Yeah, you're not going to learn anything about molecules here. Sorry about that. But yeah, relativity and the photoelectric effect are pretty important there from Einstein. Yeah, and the Schrodinger equation just gives us the shapes of the atomic orbitals. We can't use quantum mechanics for full molecules. In fact, the equation's only exact for the hydrogen atom itself. When we have bigger, more complex atoms and then molecules, we have to make approximations with quantum mechanics to get to the correct answers there. Okay, we've already talked a lot about formal charges and the structures there, the valence electrons. That helps us out. But we need to get to MO theory to begin to figure this out in a more exact way. And we'll just do a little bit of MO theory. I know there's very little of this in your book at this point. Your book actually defers this discussion until chapter 16, but we'll go through this and we'll keep it very qualitative. Hopefully you saw some of this in general chemistry. So molecular orbitals are what? Linear combinations of atomic orbitals, okay? And that should make some sense. We do it mathematically, actually, to be exact. But here it is. And remember what an orbital is. It's the probability of where those electrons are. And what's the key thing you got to remember about electrons? They have wave-like properties. So the shading of the orbitals, open and then dark shading, is not referring to charge at all. It's the wave-like properties, the peak and trough of the probability of where the electrons might be found. Now, when we construct a hydrogen molecule, which is H2, we have the duet of electrons, 2 electrons in a bond, right? That has the what? Electronic properties, electron configuration of the noble gas helium, right? That filled level 1. So starting with the simplest one here, we can make this molecule by bringing together the 2 electrons on the atoms in phase. So that's where they're undulating this way. We call that constructive overlap, okay? So if you have 2 waves that come together, wow, they enforce each other, right? And you get that enhanced interaction there. And there we form a bond. Okay, so these two electrons whirring around the two nuclei, mutually attracted there, that's covalent bonding. And we put them in the lowest molecular orbital, which we call a sigma orbital. Sigma meaning the electron density is localized on the axis between the two atoms bonded, okay? So that says sigma symmetry, we say. And that's what it looks like. But according to MO theory, we need to have the same number of molecular orbitals as the number of atomic orbitals we use. So if we have, what, 2 atomic orbitals here, we have to have 2 molecular orbitals here. One where they're brought together in phase, and one where they're brought together what? Out of phase. So that's deconstructive overlap. And if they're brought together like that, what happens when they come together? Oh, it goes to a node. There's no probability of finding those electrons at that position, okay? They cancel each other out, you can say. Well, that's kind of crazy. Why do we need this position in space? Well, that's a higher energy molecular orbital. We call it the sigma star. And that's a position in space where we can actually excite the electrons from the ground state and make the excited state of the molecule. So if we want to break apart H2, we can do it by shining light or adding heat. And that promotes an electron to the higher orbital. And then what? It can break apart, okay? This gap here is about 100 kcals per mole. It's very different energy. And what do we mean by a node here? We mean that's a position in space where the wave equation goes to 0. The probability of finding the electrons at that point, because they're out of phase, deconstructive overlap goes to 0. Now, this is the simplest example. How many people have seen that in Gen Chem in some of these terms? Hopefully a few of you. Maybe not all of you. Well, the rest of you woke up, okay. Yeah, you've seen this before. We call this the highest occupied molecular orbital for the simplest thing, the HOMO. And we call this what? The LUMO. And that stands for what? The lowest unoccupied molecular orbital. Now, this is a very simple molecule, H2. Okay. Let's go on to methane, Ch4. And I've got them on the board. And we'll go to the board here in a second and redraw the structures. But here's the problem with methane. Methane has 4 bonds, right? There's the octet of electrons, so it's satisfied. The electron configuration around carbon now approximates that of what? Neon, the filled second level. And we know from Vesper theory, those electrons want to get away from each other. And the best way, remember we did it with the balloons last time, the magic angle here is 109.5. It's not 90, it's not flat, okay? It's tetrahedral in the corners of a regular tetrahedron. So how do we get there quantum mechanically? Well, we have to mix all 4 of the atomic orbitals, the s and the 3 p's, and we create 4 new equivalent sp3 orbitals, okay? So mathematically, this is done by changing the sign of the p atomic orbitals sequentially. I can show that to you mathematically and prove that to you. Linus Pauling did this in the 1930s. He stayed up late one night trying to rationalize this problem we've just been talking about. He said, well, if I mix and match those orbitals mathematically, look, they end up pointing at the corners of a tetrahedron, okay? And he called them sp3 hybrid orbitals. They're mixed, okay? And that's okay. They go to a little bit lower energy level than the p's and a little bit higher than the s, okay? But notice there's 4 of these. sp3 means there are 4 equivalent new orbitals that point at the corners of the tetrahedron. Okay, so how do we get then the sigma bonds here to the hydrogen? Well, then we mix these sp3 carbon orbitals with the 4 hydrogen orbitals, and we get the sigma bonds right there. And there, and there, and there. They're all equivalent. So we create 4 new sigma bonds, all at the corners of the tetrahedron. And now we've solved that problem. We have the geometry suggested by Vesper, but then now there's a theoretical basis for it, mixing and matching those orbitals. So we'll review that, and we'll get to the board there and see that. What else do we create, though? We have here 4 atomic orbitals, right? And we have the 4 hydrogen 1s orbitals. So how many molecular orbitals do we actually need for methane? I'm only showing 4 here, but we really need what? We need 8, okay? So where are the other 4? Well, there are 4 sigma star orbitals up here as well. So we're only showing the sigma bonds right here, okay? But we'll get to that in a second. We'll go to the board. And there's your geometry for it, and mixing and matching the orbitals to go to the corners of the tetrahedron. You can approximate it by a cube, the opposing corners there. And you see carbon right in the middle, and this magic bond angle between the bold lines there is what? The 109.5, okay? But we'll just stay qualitative with it, okay? Not going to make you do the math for it. Okay, ethane. A little more complicated maybe. Now we have two types of sigma bonds. We have a carbon-carbon bond, and we have the carbon-hydrogen bonds on the edges, right? It's still tetrahedral geometry. There's still 4 bonds to each carbon. So here we do the same sp3 hybridization, and I'm just showing you the two here on the carbons pointing toward each other, what? In phase. So the sign of the wave equation is plus plus, meaning what? They're in phase. That's what? Constructive overlap with those electrons waving around, right? If you're a surfer, you know what I mean by waves, right? Sometimes at the beach, 2 waves can come together and all of a sudden a much higher wave, or they come together and they cancel out. Okay. There's all sorts of neat things with standing waves in water and plucked strings, right? If you're a musician, you can see the wave, that's formed by the strings sometimes. Anyway, and if you had some physics, they go over this in physics as well. Has anybody seen this, these wave type equations in physics or mechanics? Yeah, a couple people. So yeah, these are common things in science, but here's the constructive overlap, and there's our new sigma bond, sigma, and this is referring to the carbon-carbon sigma bond. Down below here, we have what? We have these carbon-hydrogen sigma bonds, which are also down here. They're a little bit more stable. I'm not showing those. And what else? We have the deconstructive overlap for the 2 carbon-carbon sp3 orbitals pointing at each other where the signs are out of phase, and that will create a node there when they're brought together, right? We have the deconstructive overlap, and we have the little nodes, tips pointing toward each other. That's to minimize that interaction. And notice the sigma star, the lobes become very large on the back side of those carbon atoms, okay? And that's a position in space we'll look at when we do reactions coming up. We'll use some of this theory later on for reactivity. It's not just to explain the shapes. But here we have the HOMO and the LUMO here. Then we also have the sigma stars for the carbon-hydrogen bonds up here, right? So that's ethane. Questions on methane and ethane so far? sp3 hybridization, okay? Means 4 new bonds on carbon, okay? 4 new molecular orbitals, corners of the tetrahedron, sp3. They're all mixed together equivalently, and they all create the equivalent orbitals of those carbons. All right, how about the next one? Ethylene, C2H4, okay? The next one over. And there we have a double bond between the 2 carbons. So we're going to mix just 3 of the atomic orbitals, the low energy s and just 2 of the p's. And we're going to create 3 equivalent sp2 orbitals. There they are. And the pz is left alone. It's still at this upper level right here. Okay? Doesn't matter whether it's px, y, or z, as long as the geometry of the 2 are sideways to each other. And you'll see that when we put it together here. But 3 are equivalent, sp2 hybridization, and then 1 is left behind there. Here's what it looks like. The hybrids are in orange there, trigonal planar. They're all in a plane. And then here's the pz left behind, okay? These are just the mixing of those atomic orbitals to create the correct geometry we need for a double bond up here, you can see. And then what's the consequence of that? Well, we bring together between the 2 carbons there's our sigma bond, and that sigma bond's formed between which orbitals? 2 pi's, 2 p orbitals, or 2 sp2s? It's 2 sp2s, right? And there it is, right? Sigma density right on the axis. So that is indeed a sigma bond that arrow is pointing to right there. What do we have left behind? We have the 2 pz's, which are blue there. I don't have the shading. We'll get to that in a second too. You'll see both the pi and the pi star, where they're in phase and out of phase. And then on the sides, we have the carbon-hydrogen sigma bonds also. So we have what? 1, 2, 3, 4, 5 sigma bonds and 1 pi bond, top and bottom, okay? When it's brought together in that way, we have a pi bond that looks like this. Remember from ChemTube, I showed you that animated thing, and you can go, how many people went to ChemTube to check out some of those structures? I talked to a couple of people yesterday. Yeah, do that, or, your models, whatever. You have a lot of resources to physically interact with this. This is what it looks like. This pi bond is top and bottom here. It actually goes to a node right at the axis between the carbons, okay? And that's what? The electronics of a p atomic orbital. And now a molecular orbital, a pi bond, you see is top and bottom. Are the electrons on top, or are they on the bottom, or both? What would you say? Because 2 electrons go into that pi bond, right? Are they on top, or are they in the bottom? Or is one on top and one on the bottom? What would you say? Anybody? Yeah. It'd be what? Could be anywhere, could be both. Well, how do they get from the top and then go to the bottom if there's a node right at the plane where the carbons are? They can travel over. The term in quantum mechanics is called tunneling. Don't worry about that, but it can actually skip over a position where there's 0 probability of where they can be found. They're found top and bottom. They're spin paired, okay? But it occupies the space both top and bottom for that pi bond, okay? Which is kind of a neat thing. It's called tunneling, but yeah, it can cross over that barrier where there is a node within the molecule with a probability it goes to 0. Here's what it looks like. There's my lame pi bond. Do you like that? Kind of looks like 2 sausages. Sorry about that. Or 2 bananas, maybe. I don't know. They used to be called banana bonds. We don't like that now. They're pi bonds, okay? Top and bottom. Here's the sigma. It's lower in energy. And here's the pi, okay? The next step up. That is indeed the HOMO of this molecule. The LUMO is the pi star. There it is. It kind of pushes the lobes out, and they're brought together, what? Out of phase, right? And there's another node right there. These dashes mean nodes within the molecule. And then we have the sigma star, which is this sigma bond just brought together out of phase, and that's right here. That pushes those 2 lobes toward the back. And that's indeed the sigma star. Notice there's kind of a mirror plane relationship. The low energy ones are the sigma, the higher energy ones are the sigma stars. At the interface is the pi and the pi star. Why is that? See if you can get a feel for that. It's kind of a intuitive thing, I'd think. What does sigma density mean when it shares those electrons? It's shared where? Right between the 2 carbons, yeah? And so that's going to be a stabilizing effect. You can say they're closer to the positively charged nuclei, and those electrons are spin paired. And yeah, they're shared, in this position between the 2 carbons. And that's a stabilizing effect, right? That proximity, I think, to the nuclei, which means if they're out of phase, that's a higher energy interaction. And then we have the pi bond in phase, which is off the axis. It's above and below. Okay, there's a node right there. Then the probability goes to 0 at that point. The 2 electrons are spin paired. I'm showing them in top and bottom. That's just to show you, where they came from. There was an electron in each of these, p, z orbitals right here. And there they are now. They're actually spin paired, and they can be at top and bottom, that tunneling effect. And then that's a little bit lower sigma or pi star than the sigma star, okay? Because it is off the axis there. But anyway, HOMO, LUMO, so know those terms and just the relative position energy-wise, okay? Okay, what's the next one? Triple bond. So yeah, we'll do the models and go to the board here in a second too to help you draw this. So typically for the test or quiz, you need to be able to draw geometry-wise, these basic types of forms, and then say, what hybridization's involved and what type of bonds are involved, okay? So it's a little bit of artwork to reproduce these things, but I'll help you out, okay? I'm no good at it, but I can usually get through it, okay, and help you out. But here it is for digonal geometry or triple bond. What I mean by digonal, the carbon's bonded to 2 things, right? And what's the angle again? 180, okay? So we just did 109. We just did 120. I should have mentioned that for sp2 hybridization, right? That's the trigonal planar. So I should have reviewed that, sorry. And then what's our geometry here for digonal? It's 180, right? Okay. So here it is. We hybridize what? Again here, and we mix the S and the 3 P's. Again, here's our starting point up here. Sorry, my graphics a little lame, I guess. We're mixing an S and just 1 P, and we create 2 SP orbitals. And we leave behind the PY and the PZ, atomic P orbital. Okay, so we're consistent here. And this was a real aha moment for Pauling, right? Because his idea of mixing and matching orbitals, doing the hybrid effect, finally rationalizes it with Vesper theory. And he was in X-ray crystallography. He knew the geometries of molecules he was seeing by X-ray analysis. So this was really good for him to bridge that gap between atomic orbitals and then the molecular shapes. It was a real breakthrough. That's why he won the Nobel Prize, okay? The structure of all organic compounds and inorganic. This applies across the board, and to materials as well. We talk about conducting materials. We have the band gap distance between the filled orbitals and the empty orbitals. And if that gap gets too small, it becomes a conductor, okay? So this homoluma thing actually applies to metals and a lot of other materials, surfaces and things. So it's a universal theory here. But so here's the 2 SPs, right? And the 2 P atomic orbital. And again, my coloring here is consistent. Here's 1 SP orbital right here, this orange one. And here's another one right here on the other side, okay? So those are 2 orbitals here. And then the P's, you know, top and bottom, that's just 1 right there, the PZ. And then the PY, that's the other one right there, okay? So that's a little confusing. The 2 SPs are pointing opposite of each other, okay? When you just mix the S with the 1 here, I guess the PX, okay? You mix it together with the shading reversed, and you see that's the 180 geometry, just using the 1 PX orbital, changing its shade, mixing it with the S, okay? And Pauling did that mathematically, and he said, aha, that goes to 180. They're opposite of each other, okay? And then, you know, different views of it, top and bottom. And here it is, into the 2 SPs. Yeah, I clarify that a little bit more here. This is 1 here and then 1 here, okay? And then what does it look like when we mix it? The triple bond? Yeah, it looks like that. That's not very helpful, is it? Well, here we got the 2 of them pointing right toward the carbon. That's the new sigma bond there. And then another sigma bond over here to the hydrogen. And then we have 1 pi bond here and 1 pi bond here. In the models and going to the board, that'll look a little more clear. We can also look at these with the computer simulations to look at the electron density. These are electron density maps, which come out of those calculations. Red means high electron density. Blue or green is neutral. Blue is low electron density. Okay, so it's kind of a colorized shading thing here. Can be done mathematically, but here's for ethylene. You see the pi bond, the nice dark red top and bottom. And then ethylene is kind of barrel shaped. They're kind of all interacting, but the pi bond top and perpendicular to it there. And then the 2 hydrogens on the end actually have blue shading. Acid-base chemistry in chapter 2, we'll get into that a little bit. And then benzene, if they're all conjugated, it forms kind of a donut type structure there. Okay, yeah, bond lengths and angles, we'll get to that. And electronegativity is our last topic. But let's go to the board now and draw some of these here and review, you know, what we're talking about the different hybridization states. And so, you know, we mix here for what? sp3, and there's 4 of them, okay? And carbon, you know, forms the new sigma bond to each hydrogen. So here's 2 that are in the plane, and then we have, you know, 1 here coming out. Okay, so that should be kind of bolded there. And then we have 1 going back like that. And they have a little bit of a lobe on the back side of them, you know, which is kind of a vestige of what the p orbitals were when they're mixed there. But our angle here is what? Again, 109.5. And then we can look at what's called an orbital diagram for this also. So we have the carbon hydrogen sigma bonds, and what? Those are all filled. So those are your 8 valence electrons from the carbon and the hydrogen. What do we also have though? we also have these sigma stars, okay? And there, for each one of these, let me just draw one. So a carbon, hydrogen sigma star would look like this, where there's a node now right between the two atoms, okay, right on the axis. And that's what these look like. And they're positions in space. They're superimposed on the bonding orbitals. If we excite this molecule electronically or thermally, we'll promote an electron to the anti-bonding position. And that's where we can begin to break a bond. So reactivity comes out of this MO theory stuff. Okay, questions on methane? Is that showing up okay there, Colin? Okay, good. Let's look at ethane. So yeah, we did this one here, and what? It's still all what? SP what for ethane? SP3. Very good. And each one of them, is pointing right here. I'll just draw the sigma bond, which has that geometry there. Sigma star. We could do the diagram for this one too. Only we'd have what? We'd have 6 here for the sigma carbon hydrogen bonds, and they're all filled. And then, and they're more stable actually. They're about 100 kcals per mole stability values. And so what's our other sigma bond here? It's the carbon-carbon sigma bond, and it's right there. And then we have the sigma star for the carbon-carbon bond, and then we have the 6 sigma stars for the carbon-hydrogen anti-bonding position. Okay. Does that make sense? So sorry I didn't fill it in or do the whole geometry there for that. The important one I think is ethylene. Let's get to that one. So ethylene, how are we going to draw that? Well, carbon-carbon bond, trigonal planar. So from VSEPR, we can come up with a geometry right here and not worry about the pi bond yet. Okay, Pauling, of course, worried about it. You need to worry about it now. What else do we need to draw here? We need to draw the pi bond. And let's draw the pi, not the pi star. We can draw that. Okay, so what would the pi look like? It'd be where these PZs are brought together what? In phase. Okay, so that's our pi bond, both top and bottom. Okay, and there it is in all its glory. Well, stick figure anyway. So red in phase there, blue in phase, and then trigonal planar for all of the atoms there. All 6 of the atoms are in a plane there. Pi, and then pi star. We need to look at the pi star, which is out of phase. It's higher in energy. It would look like this, where we have another node between the carbons. We already have a node right here. And remember, a node is a position in space where the wave equation goes to 0, or what? The probability of finding electrons is null, 0 also. So what would our diagram look like here? We've got the carbon-hydrogen sigma bonds, right? And they're all filled. 8 electrons in there. What's our next molecular orbital up? Come on, somebody's got to help me. Carbon-carbon, yeah. So there it is, CC1, and it's filled too. What's our next one up? It's going to be the CC pi bond. Okay, this is the sigma bond, and that pi bond's also filled. Okay, so there's all the bonding ones. Going up further, we have the pi star, and that's the next one up. Then we have the sigma star, and then we have what? The 4 sigma stars for the carbon-hydrogen bonds. So this sigma star is carbon-carbon, and this pi star is carbon-carbon, the pi bond. Yeah, it looks more complicated. So yeah, I don't expect you to do these diagrams. Well, the simple ones I think you can follow, okay? I'm not gonna rigorously go through a bunch. And this is the energy levels going up higher and the positions in space. This is important to know, I think. What do we call this one? The highest filled one? That's our HOMO. And indeed, this is our LUMO right there, the pi star. And that's where a lot of reactivity occurs, okay? So the pi bond will react before the sigma bond. And we'll see that coming up in a later chapter with reactivity, okay? So those ones that are at this interface between filled and empty are the important ones. Okay. All right. So that's ethylene with a carbon-carbon double. How about this one? This is carbon-carbon digonal geometry, right? It's only bonded to two things. So what's our bond angle here? 180, right? And this is a sp orbital here and an sp orbital here, okay? So we've got one there, and they're opposite of each other. And then we have this one over here, which is the other sp orbital on this carbon pointing toward this hydrogen. So you can already get the 180 digonal geometry there. Well, it's left behind. PZ, okay, and P what? PY or X, doesn't matter. Let's look at the bonding ones. So top and bottom, that's one pi bond. I told you this would get messy. I'm a lousy artist. I'm sure you guys will draw this better than me. But know the geometry and the position space and what we're talking about. Two pi bonds and a sigma bond make a triple bond, right? A double bond is made by what? A sigma and a pi. So here they are. We just drawn this one. And how about this one here? The other one on the side is yet another one front and back. So maybe I ought to draw that one darker right there. And then this in the back dashed. Okay. So have some geometry to it, the best you can, right? So let's see. There it is. Okay. So sorry, I got gray and yellow. Maybe that's not showing up too good for you. Anybody colorblind out there? I went through this once with the blue and the red, and somebody said, I can't see those at all. Oh, well, maybe you're colorblind. Yeah, it turned out can't differentiate too well there. So make sure you can see that model-wise. This is a pi bond, right? Because they're in phase. What would the pi star look like? Be out of phase. Okay, shading's opposite. So the models are cool that way. You can see the arrangement. And there it is. For that one, we can do the diagram here. We got the carbon hydrogens. There's only two of them. What's our next one up? The carbon-carbon. And then we have the two carbon-carbon pi bonds. They're degenerate. They're both the same energy. They're both filled too. And then we have the two pi stars, right? Which are also degenerate, same level. And then we have what? The sigma star. And then the two sigma stars there. So we got the symmetry going on there. It's a nice thing about MO theory. You can see that okay. Questions on that? Let's do a couple more. Talking about hybridization. So let's see. I like to do maybe a couple here. How about this? CO2. And how about this? Carbon with a cation there. How about carbon with a anion? How about nitrogen with three bonds and a lone pair? And how about this nitrogen here where it's what? Resonance conjugated to a carbonyl. Let's look at the hybridization of the carbons and the nitrogens here. Yeah, you can look at hybridizations of nitrogen and oxygen also. CO2, what are we going to say there? Carbon bonded to two oxygens. You can already say, well, it's only bonded to two things. So it's what? It's going to be digonal, 180 degrees. And what? Two pi bonds here, okay? And two lone pairs. What does it look like geometry-wise, though? And what's the hybridization of that carbon? Can anybody tell us? What is it? SP what? SP3, 2, or just SP? S what? Speak up. What do you say? SP, okay? Just SP, okay? And let's see. So we create the two orbitals there. Okay, these are your SPs. Then we have left behind what? A P here. Okay, and then we have the PY or PX, PZ, doesn't matter. Okay, so we have one pi bond here, sigma bond, sigma, and then what? The other one is over here, 90 degrees to that other one. Okay, so indeed, this carbon is what? sp hybridized, okay, to give it that diagonal geometry with 2 on there and 2 pi bonds on the side. To oxygen now, okay? So the oxygen still has the 2 lone pairs on it, okay? Like that. So what geometry you could say there, hybridization of that oxygen, you would call that sp2 hybridization for the oxygen, okay? It's pointing here, and then it's up and then down there for the lone pairs. That's what? Trigonal planar geometry around the oxygen. And then the pz, or the py, well, it doesn't matter. There's 1 p atomic orbital left behind on the oxygen, right? To interact as a pi bond with the carbon, okay? What about a carbocation? How many things are we bonded to there? 3 coordinate. So what does that mean for the hybridization? Well, there's an empty orbital on carbon, right? What's that empty orbital? It's actually a what? A p atomic orbital left behind. It's the same geometry you use for ethylene, right? And these are all trigonal planar. So it looked like this, right? One of them coming out, one of them going back, and one in the plane there. So there's the 3, sp2 orbitals that we rehybridize, and then the empty p atomic orbital bears the plus charge. But it is trigonal planar, sp2 hybridization for carbocation. Does that make sense? Fits into the theory we just talked about, okay? And this is a real home run for Pauling, right? It applies to reactive intermediates also. How about with a carbanion here? Now we have an extra ligand on here, right? A pair of electrons making it negatively charged. So how many total groups do we have around this carbon? 4, right? So what type of hybridization do we need? Not trigonal planar. We need what? Tetrahedral, right? So the geometry around this carbon would look like this, right? And that well, this would also be in a plane, but it's down there. And so what's our bond angle here? 109.5. Okay, and it's tetrahedral. So that's in an sp what? 3 molecular orbital. Okay, and then the sigma bonds are all made here with sp3 orbitals. Okay, does that make sense? What about this nitrogen? Same thing here. It's neutral now, right? It's an amine. We'll look at amines later coming up. 4 total groups, so we need 4 coordinate, which means what? It's also sp3. Then we can just do the geometry right here, right? There it is. This is in the same plane as the other group there. But yeah, this lone pair, you'd say is sp3 hybridized. It's what? Tetrahedral, okay? Now, what about this lone pair? That's a little bit different. We could say, what, 1, 2, 3, and then 4, the lone pair. Trigonal, planar, or tetrahedral. What's the geometry there? I'll give you a hint here. It is indeed sp2 hybridized now. And it is trigonal planar. Why? Why the difference between this amine and this amine right here? Anybody? You got an idea? Has to do with the carbonyl next door, right? So what can we invoke here? What's the double-headed arrow mean? Resonance, right? Let's go ahead and resonate this. And what would it look like? Ah, look at that. Now, how many groups do we have around this nitrogen? 3, right? And we have a pi bond here. There's a significant resonance contributor that's stabilizing this amide functional group as opposed to this amine. And we'll look at functional groups later on, don't worry. Amides are very important for proteins and peptides. What is the hybridization here? It is indeed sp2, and it planarizes that to maximize the overlap with this pi bond right here. Okay. Now, even though there's charge separation, and you could say that this is the most important resonance contributor, this is a major resonance contributor, okay? And it's seen in the geometry. It is indeed trigonal planar when we look at the geometry of that. It's a different structure, actually, than the amine. We'll see that in a couple places later on. So that's a little advanced topic here right now for you, talking about hybridization. I'd have to give you a hint to begin to think about that at this level. We'll see later on about the reactivity of amides and how they are indeed flat, trigonal planar. Okay, questions on that? Let's see, let's go back to the board. And I need to leave time to do some experiments here for you. Let's go back up here, Colin. Let's turn this on. And is that showing up? Here we go. There we go. Okay. There's our potential energy diagrams, electrostatic potential energy diagram. Bond lengths, bond angles. So hybridization affects bond lengths. Okay, I think I mentioned that before. The shortest bonds are actually that have higher bond orders. So a triple bond is actually shorter. These are in picometers. A picometer is 10 to the minus 9 meters. I prefer angstroms, which are 10 to the minus 10. That's not an SI unit, but normally you see that in angstroms. So picometers, 121 picometers or 1.2 angstroms. Okay, that's shorter than ethane, which is 1.53. Why? Why, when you increase the bond order, is the thing shorter? Anybody? You'd think you've got more electrons in there. That's more particles. How come that doesn't make that bond longer? What can you say? What's the key effect here? Anybody? Don't make me answer it. Come on. What is it? So if you have more electrons in between two nuclei, and what's the charge on the nuclei again? Positive. So the electrons function like glue, right? If you have more electrons, that minimizes the repulsion between the two positive nuclei, which lets them shrink down a little bit shorter, okay? They are oscillating, but they're oscillating around a shorter bond distance, okay? And yeah, the bond strengths also increase, and that should make some sense. We'll say more about that in a later chapter coming up. Bond lengths, if it's a carbon-hydrogen bond, again, the hybridization, this is sp hybridized versus sp2 versus sp3. This has to do with the s character in that hybridization. S atomic orbitals are closer to the nuclei. They're shorter when they hybridize if they have more s character. Not by much, but you do see that. Okay, yeah, and here's this percent hybridization for the different ones. So yeah, you have 50% S character if you're sp hybridized, whereas it's only 25. That'll have important consequences for reactivity also. Electronegativity, I need to get into this a little bit. The most electronegative atoms you remember from Gen Chem are in the upper right part, periodic table. That's fluorine, 4.0 on the Pauling scale. This has to do then with when you put those bonds together in molecules, it changes their properties. So methane, for example, is not water soluble. It's very nonpolar, whereas methanol has two polar covalent bonds. That oxygen and that hydrogen there are very polarized, we say. So that difference in electronegativity can be very significant. Let's look at the board here for a second. And I hope we can get to these experiments. Maybe not. We'll get to them. Okay. So if we have a carbon-fluorine bond, for example, carbon on the Pauling scale is what, 2.5? And fluorine's 4.0. So this difference in electronegativity is what, 1.5. Okay. So we say that's a polar covalent bond, and a lot of the time the electrons are spent on the more electronegative atom. Electronegativity because it's close proximity to the noble gas configuration, right? So fluorine is tugging on those electrons. And these delta values are referring to charge, okay? At any given time, there's more electron density on the more electronegative atom. So this is the partially negative end of that bond, partial positive end of that bond. So that difference in electronegativity. If you get higher than 1.8 for this difference here, those become ionic. The electrons are completely transferred. But if it's less than 1.8, we say those are polar covalent bonds. Let's look at a carbon-hydrogen bond. Carbon's 2.5, hydrogen is 2.2. So the difference here is only what? 0.3. We call that a non-polar bond. If the difference is 0 or up to 0.4 or 0.5, We call those non-polar bonds. So the polarization here is actually, this is the more electronegative end, that's the more electropositive end. And we can draw what's called the bond dipole moment for any bond. It's an arrow with a plus, and the plus on the back means that's the partially positive end. It's a vector quantity. It has to do with the direction and the length of that bond. But yeah, that's how we draw it. Yeah, so if the difference gets up to like 0.5, it's still nonpolar. If it's higher than 0.5 and still lower than 1.8, that's polar covalent. Okay. If it's higher, the difference than 1.8, then it's a salt. It's an ionic compound. Okay. So this range here we call polar covalent. Anything lower here, the difference is very close. We call just nonpolar covalent bonds. Okay. Let's look at the molecular dipole moment. So if we have something like this is acetone. We'd say the bond dipole moment is right here for this, and that dominates the molecule overall. We'll see the polarity of this molecule so this molecular dipole moment is a consequence of all of the bond dipole moments, but it's for the entire molecule here. Okay, so the partial negative end is up here on oxygen. You can see this with methylene chloride. We saw this before. So the difference between carbon and chloride is significant there. So we have these bond dipole moments at which we have the vectors. And then the overall dipole moment for the molecule, you see the sum of those vector quantities. And this is the partial negative end of the molecule. The partial positive end is over here for that. And we'll see methylene chloride is quite polar overall molecule-wise. And then what about this? Carbon tetrachloride. So if we have 4 chlorides here, they're all pulling in equal opposite directions. These are the bond dipole moments for the chlorides. And you see it cancels out. So overall, the molecular dipole moment actually goes to 0. Okay. Whereas for methylene chloride, because they're pulling opposite this way in the tetrahedron, and the sum is significant, this is a polar molecule. Let's see, I got a bunch of examples here where you can kind of see that. Water, we could do water. Methylene chloride, you see the polarity there. Pretty polar molecule. Formaldehyde, acetonitrile. Nitrogen is more electronegative. Then we got this chart of solvents here. See, water, a very polar molecule. You can measure the dielectric constant or measure the molecular dipole moment. And solubility in water, this is the infinite symbol. These molecules are polar enough. DMSO, DMF, ethanol, you see are very soluble in water. Whereas here, methylene chloride is pretty polar, but has kind of sparing polarity. The carbon-hydrogen bonds are nonpolar, okay? So that's some of the dipole moment. And then we get carbon tet down here. You'd think, well, there's 4 chlorides. Well, look, that has a 0 dipole moment and very sparingly soluble in water. You can examine some of these other molecules and see, their polarity is directly correlated with their water solubility, which is kind of neat there. Well, let's see, maybe I can do a couple of these experiments. Let's see, let's put some water in here and see how much we can get in there. So yeah, bring the thing over here again. Let's see, ethanol. Is that soluble in water? And I'll colorize the water with a little blue food coloring. And then we'll see here. Yeah, so that's colorizing that completely blue. And this is ethanol. And you think, well, yeah, that's a polar molecule. It mixed completely there with the water. And now, there's no difference there. It's infinitely soluble in that. But let's do another one here. Let's jump ahead to octanol. And this is an important one to see, I think. So octanol also has an alcohol, but it has 8 nonpolar carbons. So let's see here. We'll finish up with this one. Octanol has this structure. right? 8 nonpolar carbons and 1 alcohol there. So octanol, is that going to be soluble in water or not? Let's get it in there. You know, it should be able to hydrogen bond just like the OH group on ethanol. Oh, I should have used the gloves there, sorry. What do you see? You see that okay? Maybe my white lab coat. You can see the layer for the octanol separating out. It's not mixing with the water. We say it's not miscible with water. Why? Can hydrogen bond here with the OH group, but what do you have here? A much bigger nonpolar part of the molecule. So that's a little more complicated. We'll get into more of that discussion. The properties of the molecule, consequence of the polarity, electronegativity of those groups. But they can be balanced with nonpolar bonds here, which are not able to hydrogen bond with water, and that drastically lowers their solubility. So we'll end it there. Very good. We'll see you on Friday, and we'll start on chapter 2. Very good.